In the previous lecture, we talked about monoids and the usefulness of monoids. And in this lecture, we're going to look at the variation of a theme, or basically how we can use monoids in a slightly different way. And that is the monoid homomorphism. Monoid homomorphism. So, to recap, an isomorphism is a transformation from one representation to another, which preserves both structure and information. Meaning that we can by applying an isomorphism, we can turn some structure into another structure and back without losing any information. A homomorphism, on the other hand, is structure preserving, where structure is, we will see, is sort of, in this case, will be the monoidedness is the structure. It's structure preserving, but it doesn't necessarily preserve the information so that you can go back. So this is a one-way operation, whereas the isomorphism, you can go back and forth and there's nothing lost. A homomorphism might change the sort of information on the way in such a way that you cannot go back. And this will become all clear when we do a little example. So a monoid homomorphism takes one monoid and transforms it into another monoid, which is possibly quite different from the original. And we're going to have a quick little look at an example to make this clear, because this is actually not very difficult. So let's start by defining a type page to be of page of string, right? So now we've just wrapped a string, but we say this is one page full of text, and then we can define a addition operator plus for two pages, page P1 and page P2, and that's super simple. All that we do is say just page P1 plus P2. Since these are strings, we can just add them. So now we have just doubled or added two pages. So, okay. So we're gonna do there's gonna be a function here that we're gonna just say word count, which is a function which takes a string and produces an int. So, word count is a function which will just take a string and count the words in it and spit out that number. So I'm going to create I'm just going to call it page map. But so we're going to have a page .map function. It's not really a functor map since page is not a generic container. But what this map will do is it will take some function and it will take a page and it will apply the function to the contents of the page. So it's very similar to a map. So we can just assume we have this. It's trivial. It's just matching on that, pattern matching on page, or unwrapping, getting the string and applying the function to it, right? So now I can say, okay, so if I want to count the words on a number of pages, so I suppose I have n pages, I can say, well, let count equals, and I can say page.map word count, and now I have a bunch of pages. But I know one thing. I know that pages are monoids. So I have the plus operator. So I can just say P1 plus P2 plus and so on plus Pn. And I can just add all the pages and then I can count the words. So here we use the monoidal properties of the page. And it's all fine. But there's another way of doing this. And it works slightly differently. So, how could we do it another way? Well, we could just say, okay, instead of adding the pages like this, so here I add the pages, I could just put them into a list. So then I could say list map word count, of course, word count, and then I have a list of P1, P2, P3, Pn. So now I'm using the list map instead. And this will result in a list of integers. But note what has happened. These were one set of monoids, which have been turned into integers, which are also monoids. And now I can just pipe that result into list .sum and sum up all those integers and receive the exact same result as here. So here we see there's two different ways of doing it. One is that I just add up the pages directly and count. The other one is that I count the pages separately and add up the result. And this is an example of a monoid homomorphism. You see here I transform this set of monoids into a new set of monoids, which I can then do something with. And this is in fact a very clever trick. Because if I do it like this, which might be perfectly fine to do, but if I do it like this, if these are huge, this is going to be a fairly lengthy computation, and it's just going to be running this word count on this massively long string. Whereas if I do it like this, I'm going to be mapping word count on each little page separately, and that lends itself to very, very well to parallelization. So instead of saying list map, I could just say pmap, the parallel version, and I could do them on all my cores, or I could do something even more sophisticated if these things are more demanding and I have a billion of these pages. I can send them out to a cluster, do them all separately, and I will just get a list of integers back, and I can sum them up. And this is the essence of Google's MapReduce algorithm. It's just a monoid homomorphism put into action. That's basically it. A word of warning though, because it's easy to make silly little catastrophic mistakes. So instead of word count, what if I have a function which would be, I'm just going to call it frequency. Most frequent, or most frequent. We'll just call it most frequent. Most freq. And it takes a string and it produces an int. So it's very similar to word count. But this function will read a page or read a string, and every time it finds a new word, it will store it, and then it will count how many of those words are there, and then it will find which word was the most frequent. Now, what happens if I do the same trick with this? So if I first add all the pages, because it's going to be dividing to get the frequency on the page, we're going to divide by the number of words on the page, right? So if I now do the same thing, so now I take all my pages, I add them up, the whole book, and I do the frequency, I'm going to get some answer. But if I instead do it page by page and then add them up, I'm going to get a different answer. So there's something, and you can test this, and I suggest you do. So something is going on. And the one thing that you need to be careful with these monoid homomorphisms is that when you have a situation like this, that you have some f of a plus applying a function to a monoid, and you have plus some function to this other monoid, AB, it must be identical to doing the f on a plus b directly. If this doesn't hold, then note, then you will get the wrong answer. That was that about monoid homomorphism. They are important for computational efficiency, amongst other things. All right, until next time.